And good morning, ladies and gentlemen. Welcome back to the Simpkins Physics Corner. I'm Mr. Simpkins. I'm up in the corner and here with some conservation of momentum for academic physics today. This will work for anybody. But I wanted to give you some help with the homework that you had from yesterday regarding the conservation of momentum. There's a couple questions. There's a quiz for you guys to take. But you may retake that quiz. And so I wanted to show you a couple examples of how these questions go so that you can have a resource to help you out. So here's the first one. This is on these are questions 3 and 4. These aren't on the quiz. That's why I'm doing them in the video. But the strategies will work the same for the other questions. So let's see how this works. All right. So you notice in this collision we have a cowboy and a horse. They gallop down the Old Town Road. I'm gonna take my at a speed of 5 meters per second. So if the cowboy is on the horse, then they both have a speed of 5 meters per second. 5 meters per second. And we'll say that the cowboy is the first thing, so 50 kilograms. And the horse is 600. That's a beastly horse. Actually, it's not too big of a horse, but 600 kilograms. All right, so do you see how so far as we read the problem, we set up the initial scenario. This is before anything happens, and I'll draw myself a really epic horse here. Look at that amazing horse. Isn't it awesome? And then we got the cowboy, put a little hat on him there, and he's riding on the horse down the Old Town Road with a panini in his pocket, and there they are. They're riding together. So this is kind of like two objects moving together. Well, what's going to happen is the horse is going to be startled. It's going to go, and it's going to knock the cowboy off there. So let's see. Let's get a bucking horse here. There we go. All right. The horse says nope, and then the cowboy's like yeet, and he goes through the air. And he goes flying that way. All right, so what we have is the horse is still moving forwards, but the guy is like whoosh and gets shot off of the front. So the question is, it says if the horse suddenly bucks and slows to a speed of 3 meters per second, how fast? So at the end of the day, we want to solve for the cowboy's velocity. How fast does the cowboy fly forwards? Okay, so this is a collision. Or in this case, it's got an explosion, if you will. They explode apart. But the conservation of momentum principle is going to come into play here. Remember that principle is the total momentum before a collision is equal to the total momentum after a collision. All right, and so that's why I have this table set up for you here. So when it comes to calculating momentum, let's look at the cowboy's momentum first. Well, we know for all these objects, P equals mv. The momentum is mass times velocity. So we have 50, the mass, times velocity, 5. The momentum is going to be 250 kilogram meters per second. How did I get that? I multiplied those two numbers together. Why? Because P equals m times v. Same thing for the horse, 600 times 5. All right, the horse is going to bring to the scenario 3,000 kilogram meters per second of momentum with it. Okay, now look at the way we have the table set up. This is to help you guys organize the information in this problem. We have the picture, we have the individual PMV stacks for each object, and then it says total P. Well, total P is going to be the sum of the two objects' momenta. And so how does that look? Well, I'm going to switch colors here for you guys. The total P is going to be the momentum of the first object plus the momentum of the second object. 3,000 plus 250 is going to be 3,250. All right. Now, the reason I'm making that number a different color and such a big deal is because of the law of conservation of momentum. The law of conservation of momentum says that the total P before a collision, in the absence of any external influences, which we don't see in this problem, so the case holds here, the total P after has to be that same number, 3,250. So that's the number we're going to have to operate with and keep in mind as we unpack the details for the second part of this problem. Let's go ahead and continue with this problem and figure out how much momentum the cowboy has to bring to the picture. All right, well, it looks like the horse, which hasn't changed its mass, it didn't say that the horse went on a diet or anything, so the horse still has a 600 kilogram mass, but it does say the horse now is going with a velocity of 3 meters per second. So to find the momentum of the horse after the collision, P equals mv, we do 600 times 3, and that's going to be 1,800 kilogram meters per second. That's how much momentum the horse has after it bucks the cowboy off. Now, keep in mind, this number has to be true. Why? Because the total momentum always has to stay the same. Well, what does that mean? That means that however much momentum is left over has to go to the cowboy. In other words, if our total momentum is 3,250 and the horse has a momentum of 1,800, then the cowboy has to have the rest of that momentum. So 3,250 minus 1,800. The cowboy has to bring 1,450. I'm going to write that number over here. 1,450 450 kilogram meters per second of momentum to this situation. All right, this is the important part. Do you guys understand how I got to 1450? First, we found the total momentum before the collision, and then we said, well, the total has to be the same before and after the collision. Then we figured out the momentum of the object we knew about, the horse, and we said, okay, if the total has to stay the same, 3250, and the horse has 1800, then how much momentum must the cowboy have? Answer, 1450. So that's where that came from. The cowboy has a mass of 50 kilograms, and so this is going to be kind of a ridiculous answer, but the cowboy is going to be yeeting off of here for sure very fast. To solve for this, since P equals M times V, with some algebra, that means that V would be equal to P divided by M. And so I'm going to do 1450 divided by 50, and I can't see the answer in my calculator, but I'm going to go ahead and say that's 22. Oh, God. I've had this calculator since high school, and so the screen is a little rough. There we go. 29 is going to be our answer. That is a beast of a velocity, but it was a beast of a horse, giving him a beast of a buck. So why not? Final answer to this problem is 29 meters per second. So in the quiz that I gave you yesterday, some of those practice problems, I was asking you the steps along the way. So for this one, I would have said like, hey, what was the momentum of the cowboy before he got bucked off? What was the total momentum? What was the momentum of the horse after it bucked? You know, all that sort of stuff. I was trying to get you to, or I was trying to diagnose to see how many steps you were following along with. So there's one example for us, and we have time for another one here too. Let's look at a different one. This is where two objects stick together. So we have on a snowy day an 800 kilogram car going 20 meters per second rear ends a 600 kilogram compact car sitting at a light at rest. All right, so we have the bigger car here coming in, and we have the smaller car here, and it's at rest. So let's go ahead and set up our PMV stacks. The PMV stack for the first object, well, it has a mass of 800, and it has a velocity of 20 meters per second. All right, because P equals M times V, hopefully you're getting the hang of that one by now. 800 times 20 is going to be our 16,000 kilogram meters per second. That's a lot of momentum. Yeah, it is. The smaller car has a velocity of 0. So yeah, sure, it has a mass of 600 kilograms, but it's at rest, and objects at rest have 0 momentum. So when it comes to total P, that's a pretty quick calculation. The total momentum of the first car, 16,000, plus the momentum of the second car, plus 0 is still 16,000. All right, now here's the big idea. Again, the leap into the after part. The total momentum before a collision has to be equal to, if you said the total momentum after the collision, you are correct. That total number has to stay the same because that's the law of conservation of momentum. The momentum of a system has to be the same before and after our collision. Now, it says the two cars stick together, their bumpers get locked. How fast do the two cars move together immediately after the collision? So we got the big car, and it smashes into the small car, and they're moving together. Now, I'm going to do a little bit of a sleight of hand here, but I think you can follow along. Because the two objects stick together, I'm going to combine them. What do you mean? I'm going to say that the 800 kilogram car plus the 600 kilogram car, if I said, hey, how fast are they going? The answer is the same speed. They're stuck together. It's not like one can go one speed and one go the other if they're going the same, if they're stuck together. So I'm actually just going to consider this a big chunk of mass moving with the same speed because that's the reality of the situation. And so what I'm going to do here is instead of doing 2 PMV stacks, I'm just going to do 1 PMV stacks. I would caution you against over applying this too much, but if you have a situation where two things stick together, it's a perfectly legitimate strategy. So we know that the combined mass is 1,400 kilograms because they're sticking together. And since we only have 1 PMV stack, the total momentum has to be given to that big blob of stuff moving. And to be a little more explicit, the two cars smashed together. And so now we're in the same situation we were in the last problem. Since P equals mv, V would be equal to P divided by M. And so P, 16,000, divided by M, 1,400, is going to be 11.43 meters per second. All right. So I hope that in seeing these two examples, it gives you a little bit of a jump off point. You're always going to organize things with PMV stacks. You always consider the big idea as you go along through these questions. The big idea is the total momentum before is equal to the total momentum after. If you happen to have two separate objects, all you have to do is make sure that these two P's, the momentum of the individual objects, add up to the total P. And as you saw in these problems, especially for the horse here one, basically you work your way through the beginning, you figure out the total momentum. Here, let me change colors real quick so you can see what I'm talking about. You're gonna work your way through the beginning with all the information you know. You're gonna get the total momentum. You're gonna say that total momentum applies to the other side. Then you're gonna come back up to momentum and say make sure these guys add up, and then you go and fill in the details with whatever the problem is asking you for. Okay, so that's kind of like the general problem approach strategy for you guys. Hope this was helpful for you guys. If you like this video, go ahead and hit the like button and leave a little comment. You can sub to the channel Simpkins Physics Corner for more physics updates daily. But until next time, this is Mr. Simpkins in the Simpkins Physics Corner. I'm out.